Okay, now let's look at some of the examples from the pole zero plot. Say this is the representation of a system transfer function. This is RE of Z, this is IM of Z. This is our unit circle. Then say there are two poles, these 2 points. So what will be the amplitude or magnitude plot? We are going to find that. Let me draw the magnitude plot first. This is our omega. So the magnitude plot will look something like this. This will not reach 0, but rather it will tend to reach 0. So what we need to concentrate are simply these 2 points. So first of all, if you consider e to the power of j omega to be at this point, because any value on the unit circle will be e to the j omega, and for various values of omega the point will rotate along the unit circle. Say for some value of omega we are considering this point, and if you look closely, the distance from this point to this pole is the shortest. And since this value is shortest, and if you remember from the previous video, the distance di for the pole was found in the denominator, that is h of omega's magnitude was given by ri by di, running multiplication. So this distance from e to the j omega to the pole occurs in the denominator, and since this value is very small, the denominator will get smaller and consequently h of omega will be at its highest. So for that reason we get the value of magnitude of h of omega to be highest at this point. Similarly, if we consider this point over here, the distance from this pole is shortest, and hence once again we find the magnitude to be highest at this point. So one thing that should be mentioned in this plot, that is the magnitude plot, we are varying omega along the x-axis. So if omega is varied along the x-axis, in the z domain the omega will be varied in this circular axis or the circumference of the unit circle. So let us look at another example, or rather enhance this example. What we are doing now is, this being our unit circle, simply adding a third pole. So these 2 poles were present as before. So let us once again see what will be the magnitude response. This is omega. This will be our new magnitude response. So these 2 peaks were present earlier, because say this is for these 2 points, this being 1 and this being 2. So this is 1 as it is in the positive direction, and this is 2 as it's in the negative direction, that is the clockwise direction. So the third point that is found over here, point 3, comes from over here. And if you compare this distance and this distance, these two are almost identical, and for that reason the peaks occur at an identical height. This of course is h of omega's magnitude. Rather, if you look at the point 3, and this distance is very much smaller than the previous two distance, and the smaller it gets in the denominator, the larger the value will be of the magnitude. So this point will occur at a higher position or at a higher magnitude from the previous two values. So if that's the case, let us enhance the problem a bit. The third part, what we are going to do, this is our unit circle. So these poles are present. We are adding two additional poles. So we have shifted this pole closer to the unit circle. And one thing to be noticed, I have said earlier, the system we shall be considering must be stable. That is, the pole may occur within the unit circle. So if a pole occurs on the boundary of the unit circle, that is on this circumference, the system will become marginally stable, and any poles outside the unit circle will make the system unstable. So all we are concerned is with the poles all being occurring within the boundary of the unit circle. Zeros, they can occur at any place. They can be inside the unit circle, outside, or on the circumference of the unit circle. We are not concerned about that. So this is RE of Z, this is IM of Z. So let us look at the magnitude plot. The plot will look somewhat, there are 5 poles, so evidently there will be 5 peaks, and if you look upon closely, the distance are almost identical for the points that is mentioned. So if you consider this point, this point, this point, this point over here, and this point over here, the distances are almost identical, so the peaks will occur almost at the same height. And so the plot will look something like this. So there are 5 poles, and so there will be 1, 2, 3, 4, 5 peaks. So one thing that should be mentioned is that the more the number of poles that you add along the circumference, the more there will be the number of this ripple. So if we can add if we can add an infinite number of poles over here, this plot will look something like this. This ripples will get so fine that it will seem to be a straight line, and this is nothing but a form of filter which can be stated as a band pass, which looks like a band pass filter, although it is not a band pass filter because we are dealing with causal system. So all we will be responsible for the right hand side. So the plot will look something like this. So this is nothing but a high pass filter, a low pass filter. The frequency from this point to this point will pass, and these frequencies will be attenuated. So this is how filters can be designed. And Why we are using causal system will be mentioned later on. So I hope you get the fact that adding more number of poles, this ripple will get finer and finer until it becomes a straight line. Now what happens if we add a 0 to the system? So let us look at that. So this is our unit circle. So there were poles over here, this point and this point. What we're going to do is add a 0 on this boundary point over here. So the plot will look so for 5 poles there will be 5 peaks, no doubt about that. What will happen if we add a 0 at this point is, if we consider omega at this specific point, e to the j omega at this point, the distance from the 0, that is r, will be equal to 0, because at this point the 0 is occurring on the circumference of the unit circle. So the distance being 0 will give our numerator, shown over here, to be equal to 0, and consequently h of omega at this point over here will become 0. So simply this was not reaching to 0. If we place a pole over here, this will simply reach 0, and these 2 points are identical. If we go from clockwise or anti-clockwise, this will be the 2 points. So this is our h of omega. So this is how we can simply design various types of filters using changing the number of poles and zeros in the transfer function of the system. So I've shown it for low pass filter. For high pass filter, I think you can easily calculate by placing the number of poles and zeros and playing around with it, and you will get a transfer function, or rather an amplitude response, for the high pass filter. Same goes for the band pass or the band stop filter as well. Okay, if that's the case, now let us move on to our main topic, that is types of digital filters. So we shall move on to the new topic, that is type of digital filter. Okay, types of digital filters. Now, broadly speaking, digital filters can be divided into 2 categories. Number 1 being the non-recursive type, and number 2 being the recursive type. Recursion, in other words, or in layman terms, means that if a filter response goes around following a circular path, we'll show it in details. So, non-recursive filters are otherwise known as FIR, or finite impulse response filters, and recursive filters are known as IIR, or infinite impulse response filters. So now let us look at IIR filter in details. Okay, now suppose we have a transfer function h of z to be equal to b naught z cube plus b2 z squared plus, this is b1, b2 z plus b3 divided by z cube plus a1 z squared a2 z a3, and that's it. Now what we are going to do is divide the numerator and denominator by z to the power of 3. So the numerator will become b0 when divided by z to the 3 becomes 1 plus b1 z inverse b2 z inverse 2 b3 z inverse 3. Consequently, this becomes 1 z to the 3 divided by z to the 3 will be 1 plus a1 z raised to the power of minus 1, a2 z raised to the power of minus 2, and a3 z raised to the power of minus 3. Nothing out of the ordinary has been done, just simply dividing the numerator and denominator by z raised to the power of 3. Now, from here we can determine the corresponding difference equation. And to do so, we can write h of z as y of z over x of z, where y of z is the output and x of z being the input. The right hand side will remain same, b0 z raised to the power of 3. I am working with these values, plus b1 z squared plus b2 z plus b3 divided by z cube plus a1 z squared plus a2z plus a3. Just using the cross multiplication, we can write y of z times z cubed a1 y of z times z squared plus a2 y of z times z plus a3 y of z. Similarly, in the right hand side, b0 x of z times z cubed x of z times z squared and b2 x of z times z, and finally b3 x of z. Okay, now once again dividing both sides by z raised to the power of 3, we get y of z a2 y of z inverse, this is a1 a2 y of z inverse 2 z inverse 3 b0 x of z b1 x of z times z inverse x of z times z inverse 2 b3 x of z times z inverse 3. Okay, so moving on, what we need to do is just apply inverse z transform to both sides of the equation. So we will get y of z to be y of n, and taking the rest of the coefficients, that is the rest of the value of y of z, to the right hand side of the equation, we get minus a1 y of z times z inverse 1 is a shifting property. This will be y n minus 1, and consequently a2y n minus 2 minus a3 y n minus 3 plus b naught x of n b1 x of n minus 1 x of n minus 2, consequently b3 x of n minus 3. So now this can be generalized. Say this can be generalized. So y of n can be written as, see, there are a limited number of poles and zeros, that is limited power of z of 3. Limited power of z, that is z raised to 3 is the highest power of this polynomial and this polynomial as well. But this might not be the case. The power may be same for the numerator and denominator. It can be different for the numerator and the denominator. And the number should not limit to 3. It can be any number from 0 to infinity, as long as it is an integer. So this can be simply written as summation bk x of n minus k equal to 0 to capital M minus summation of ak y of n minus k equals 1 to capital N. So in our case, if we want to get this equation, simply replace m by 3 and n also by 3, because m and n dictates nothing but the highest power of this polynomial in the numerator and the denominator. So this is just a generalized form for any arbitrary values of m and n. And this is y of n, and similarly h of z can be written as summation where k goes from 0 to m bk times z inverse k by summation k goes from 0 to n, let it be 1 to n z inverse k, and so it is. So h of a can be written in this form, and this form is brought over here from this expression. So if we once again take the value of m to be 3 and n to be 3 and plugging in the values of k, you will get up with this expression. Let us verify using one value. If k is 0, this is b of 0, z raised to the power of 0 is 1, so we are left with b to the b of 0. So this is our first value. Similarly, we get for all the values. So this is h of z. Now, otherwise, h of z can be written as, this is another way of writing simply. Otherwise, h of z can be written as b naught running multiplication where k goes from 1 to capital M 1 minus ck z inverse divided by running multiplication k goes from 1 to capital N 1 minus dk z inverse. Now this can be simply written. Say let us expand this. So h of z, they're coming from here to over here. H of z can be written as b naught times one minus c1 z inverse minus c2 z inverse 2, consequently 1 minus cm z inverse m, 1 minus d1 inverse 1 d2 z inverse 2 minus dm z inverse n z inverse n. So if we are to multiply the numerator and denominator by z raised to the power of, before that say m equal to n equals to n. So if we multiply the numerator and denominator by z raised to the power of n, we get b naught z raised to the power of n z raised to the power of n. This will become z minus c1 z minus c2 z minus cm. This becomes z minus d1 z minus d2 z minus dm. So these are the factorized form of a polynomial, and simply if you multiply, this two will get cancelled out. If you multiply this polynomial on the numerator and the denominator, you will get a form of something like this. So in this case, there will be 3 terms of z, 3 factors of z. But in the generalized case, we should not limit the factors to be 3, rather we limit it to be n. So this is nothing but, so this formula is nothing but a factorized form of this expression over here. So I hope you understand the mathematical aspect. So now let us move forward. So all this calculation from this point onwards were just mathematical calculations. All we are concerned is with this difference equation that is found over here. And upon closer inspection to this difference equation, it is seen that we get the difference equation to be a sum of the weighted inputs of both present and past. That means we get the difference equation y of n as the sum of the inputs. This is the present input and the past inputs. This is the input 1 sample ago of the present input. This is the same input 2 samples ago, and this is the same input 3 samples ago. So this is one part. Similarly, we get the difference equation as the weighted outputs of the past samples. That means the difference equation will also consist of weighted values of the past outputs. So this is the output 1 sample ago of y of n, this is the output 2 samples ago, and this is the output 3 samples ago. So if we are giving the past value of output to the system, so if this is our system, this is our input, this is our output. So for getting this value, what we need to do is return this output value to the input value. Is it not? So for this reason there is a circular loop occurring over here, and hence we conclude that the IIR filter is a recursive filter. Or in short, in case of an IIR filter, the system output will always depend upon the past inputs and the past outputs for an IIR filter. And if you look at the FIR filter that we will be showing in the latter part, it will only depend on the past inputs and not the past outputs. And for this reason, the FIR filter is the non-recursive filter. So this is the summary of what we have been doing. So now, in order of deriving the difference equation, two revelations occur, one of which being, if we give an input to the system, a single impulse function, due to the nature of the IIR filter, this past value will always be present, and essentially what will happen is this impulse signal will repeat infinite number of times in the output, hence the name infinite impulse response. Also, the second revelation is that IIR filters can have poles and zeros at any arbitrary location. So here it is seen from this polynomial and this polynomial, if this is rather I should say this polynomial and this over here, if we factorize them, we get some form like this. So here the poles can occur at any of the positions. Of course it should be within the unit circle, but any position in the unit circles. The zero on the other hand can position itself at any point on the pole zero plot, whether inside, outside, or on the unit circle. Say if there is a pole, if there is a pole at 0.3. So the position 0.3, say this is the unit circle, this is 0.3. So 0.3 in the z domain can be written as 0.3 raised to the power of n, and for whatever being the value of n, this 0.3 will go on forever. As the value of n increases, this will start to decrease but will never reach 0, although it may come very close to it. So these are our characteristics of a IIR filter, or otherwise known as the infinite impulse response filter. Now let us go to the FIR filters.